few lectures. So I'll give you guys some time to write on a piece of paper and try out a few problems on your own as long as we have time. And we'll just talk over general neutron physics. So here we go. What is a neutron? It's a subatomic particle in the nucleus of the atom. You've heard quite a bit about this from Stefano a few weeks back, but it's within the nucleus and it's bound to protons, and it has an associated mass. The mass is a little more than 1 atomic mass unit, and it's an equivalent of 940 almost MeV per c squared. There's 3 different flavors of neutrons. These neutrons have a rest mass energy, which I just told you, the 940 MeV per c squared. And there's different energy ranges, which apply well to neutron reactions. There's low energy thermal neutrons, which are far less than an electron volt, an EV there, or 0.025 EV. And there's epithermal neutrons, which are more energetic than thermal neutrons, but still less than 1 MeV, which we associate with fast neutrons. And then there are fast neutrons that are greater than 1 MeV. With moderation, you can decrease neutron energies, but when you find neutrons from a radiation source, they're typically going to start fast. So you have to use material to get them to these lower energies to moderate them. So that brings me to neutron sources. Neutron decay, does it exist? In some ways it does, but not in the general sense that we think about radioactive decay. You can have a gamma source like cesium that just decays into barium, like you see here on the scheme on the left, and that emits that 662 keV gamma ray. There's not really isotopes found in nature that decay neutrons in the same way. And the reason being, the binding energy of the neutron in the nucleus is so large that the excitation energy you would need, that the cesium is in an excited state and emits this gamma ray, the excitation energy that you would need for a neutron source would need to be much larger in order to have a neutron emission like this. And we're talking on a scale of MeV, as you can see on the right here. For smaller nuclei like hydrogen, the binding energy is not so large, so you can free these neutrons a bit more easily, but it's still on the scale of, you see 1 up to 9 MeV there, and then when you get past iron, this starts to drop down, and we get to our actinides, uranium on the far left, as we increase the nucleons in our nucleus, and this binding energy still stays on the scale of 8 to 9 MeV. But there are less conventional ways that we can get neutrons from radioactive decay. And the first one I'm going to explain to you is spontaneous fission. There's the isotope californium-252, which produces 3.67 neutrons per fission. And this is a man-made isotope. You need very high radiation facilities in order to even create this isotope in the first place. And the chance of it emitting neutrons out of all the other decay schemes it can go about, like alpha decay, is only 3% for each decay. But when you have a sample of californium, it's very active, very unstable, decaying quite quickly. So you can have a very high amount of neutrons per gram of this material. You can see here, 2.34 times 10 to the 12th neutrons per second per gram. So that's quite an active neutron source. When we have this in the lab, you only need micrograms to conduct a decent experiment. And sometimes you can have up to milligrams, but those are very strong sources. And the average energy you'll see from californium spontaneous fission, that's when the atom splits, is 2 MeV. And you can see a spectrum off to the right of what the neutron energy from californium fission can be. So it's a distribution. Each fission is going to emit different amounts of neutrons, which you'll learn more about later, not in this lecture. But from fission, I'll tell you a little bit about induced fission later, and we can talk about the fragments. But you get this whole spectrum of neutrons. There's also another man-made isotope that's more common in nuclear reactors called plutonium-240, and that produces less neutrons per fission, and it has a much lower chance of spontaneous fission, but it does still produce neutrons from spontaneous fission, and you get about 1,000 neutrons per second per gram for this material, with about the same average energy. The next neutron source we'll talk about are alpha N sources. So these sources, they emit alpha particles into an alpha absorber that then emits a neutron. So you can see here a diagram of a PUBI source. Plutonium decays by alpha decay, and sorry about that. Plutonium decays by alpha decay and produces uranium-234, and this is from plutonium-238. And we emit that alpha, and we have it in a matrix of plutonium and beryllium, so it can go on to then collide with a beryllium atom, specifically beryllium-9, and then it will produce a carbon-12 and a subsequent neutron. And the average energy of the neutrons produced from this reaction is about 4.5 MeV. You can also see another scheme here for plutonium-239 alpha decay, but both would go on to then produce alphas that are absorbed by the beryllium and then produce a neutron. There are other alpha N sources as well, like AmB and AmLi. So beryllium is that neutron absorber and plutonium is that alpha emitter. There are also americium for the alpha emitter, and then you still have beryllium as the neutron emitter and the alpha absorber. So it's the same average energy, but we get a different alpha decay, americium-241 to neptunium-237. And then we also can have AmLi. So AmLi is a lighter neutron absorber, or sorry, alpha absorber that then emits neutrons, and it has a lower average energy of 400 keV. But again, it's the same alpha scheme as AmB, just a different alpha absorption and then different energy neutron emission. On the right, you can see an example spectrum from plutonium-beryllium alpha N source, and it's not like the spontaneous fission source where we saw that nice smooth Watt spectrum. It's very jagged, and that's because there's lots of different energy states going on between the two reactions. But this is what you might see for a PUBI source. It would look identical for the AmB source, and then the AmLi source would be a lower energy version of what you see here. So we talked about spontaneous fission and alpha N sources. Those are the two most common, but one other one, which is less common, but still possible, is a photoneutron source. You can take advantage of photonuclear reactions to produce neutrons from those same alpha absorbers we saw earlier. The example you see here shows sodium-22 beta decay that then goes on to excite a neon in the center matrix, and then the neon produces a high energy gamma that can then excite the beryllium-9, and it causes the beryllium-9 to emit that extra neutron. We can also see the same thing with deuterium, as you see below. So naturally, these atoms of beryllium and hydrogen aren't going to be in these excited states and emitting neutrons, but you can cause them to emit the neutrons with photonuclear interaction. Then we move on to a more common one, the accelerated particle fusion. It's a fusion reaction of either DD, which is that hydrogen 2 there, or DT, so hydrogen 2 and hydrogen 3. And what we do here is we have this very excited beam of plasma deuterium or deuterium and tritium, and we hit a target of deuterium or tritium. And this produces very high energy neutrons, the DD reaction 2.45 MeV, and the DT reaction 14.1 MeV on average. But you have to meet, the reason we need this plasma, this incident plasma onto our target is the threshold of the reaction is very large. You can see here the approximate threshold for DT is about 4 keV there in the center of mass scenario. And the the initial energy needed for DD there is about 7 keV. On the bottom right, you can see an example from a facility out in Wisconsin, SHINE. They produce neutron sources, and they're also a large nuclear science group. But you can see the beam on the left the deuterium or tritium target in the center, and then the resultant neutron beam, as well as the remaining plasma. The neutrons would be invisible, but we still see that excited air in the surrounding area. So now that you know a bit about neutron sources, we'll talk about neutron interactions, and we'll go into a few exercises. We'll first start talking about neutron scatter. You've heard about Compton scattering for gamma rays. We'll talk about elastic scattering for neutrons, where the kinetic energy and momentum are conserved. And we'll talk about inelastic scattering, where only the momentum is conserved. Then we'll go on to a few absorption reactions, but I'll save those for later. So for elastic scattering, it's pretty simple. I'll give you an example here of a neutron scattering off a hydrogen atom, which uncharged would just be a proton. And you see the resultant scattered neutron, scattered hydrogen. Kinetic energy and momentum are conserved, and we get this equation for the recoil nucleus. For hydrogen, this A here in our recoil equation is just 1. The A represents the neutron number, which is that top number on our helium atom. So it would just be 1 to 1, this ratio with the cosine squared factor. And theta can range from 0 to 90, and that's the separation from the center axis of our recoil nucleus. So I want to give you an example question here. What are the minimum and maximum recoil energies that we could have in this neutron elastic scattering, where the neutron is recoiled off the hydrogen if the incident neutron has an energy of 2.45 MeV? And again, you have your recoil equation here. You have your range of theta, and A is equal to 1 in this case. And here's a little screenshot of the diagram as well to help you out. But I'll give you a minute or two, just put it in the chat what your answer might be. And if I don't get any responses, we'll just move on. But I want to see what you guys have to say. Ben says 0 to 2.45. That's not wrong, but what are the minimum and the maximum? That seems more like a range to me. Yeah, Ahmed's got it. So the minimum is when theta is, oh, sorry, that's actually backwards. So the maximum would be when theta is 90. And the minimum would be when theta is 0. But we pretty much have the answers there, so I'll keep moving on. Sorry, I misspoke there. Theta 0, you're correct, is the recoil maximum energy, and the minimum is the theta 90. But based on conservation of energy, the recoil nucleus can either be the maximum at 0 of 2.45 MeV, or the minimum at 90 of 0 MeV. And then we can also have inelastic scattering reactions. So we won't go through an example here because it's a bit more complex. There's a lot of different examples we could provide. But what happens in inelastic scattering is a neutron can be absorbed and re-emitted from a compound nucleus. So instead of just immediately scattering off the nucleus, we have this intermediate compound nucleus state. And because of this, some of the energy, instead of just being completely recoiled onto the nucleus, it's absorbed by the nucleus and then emitted in the form of one or multiple gamma rays. This inelastic scattering reaction requires much larger incident neutron energy than elastic scattering. That can happen at very low energies. So we have to meet some sort of threshold depending on the nucleus. You can see a few examples on the bottom right. We see lithium and beryllium on the left require 2 to 3 MeV for that excitation state. You have to get it at least to the first excitation state of 1 MeV. And then the uranium-238, as we get to our larger isotopes, do not need as much initial energy to get to that initial excitation state. Talking 40 keV just to get to that 50 keV excited state. And that has a bit to do with uranium itself already being a bit excited. It's a low cross-section for smaller nuclei, so you're not very likely to have this on the lithium or beryllium, but you can. And it's impossible to occur on hydrogen. So we've talked about the elastic scattering and inelastic scattering. Now we'll move on to a few absorption reactions. First, we'll talk about radiative capture. It's when an atom absorbs a neutron, causing excitation, and then it de-excites by emitting a gamma ray. The radiative capture reaction, you can see an example here. A neutron is absorbed by plutonium-239, so it becomes plutonium-240 in an excited state, and then it immediately emits a gamma. It's the most probable interaction in most materials, causing attenuation and shielding for neutrons, and it's used in indirect detection techniques like activation foils. Foils are most commonly metals that do not fission. The example that I gave you is an isotope that can also fission, so there's other reactions going on. But we can use isotopes like cobalt for lower energy neutrons, and we can use magnesium for fast neutrons. There are a lot of other examples as well, but I just give you two here. And we can see again the process diagrammatically of the neutron being absorbed. Plutonium becomes that excited state, emits the gamma ray, and goes back to a ground state. The next reaction we'll talk about for absorption is capture transmutation. An atom absorbs a neutron, causing excitation, and then de-excites by emitting a particle, which could be an alpha, a proton, etc. So here's one example of a capture transmutation reaction. On the top, we have a neutron being absorbed by a helium-3 atom, and then it emits a triton, which is a tritium, a hydrogen-3 atom, and a proton. Another reaction that we can have is neutron absorption by lithium. So lithium-6 absorbs a neutron, and then emits a triton and an alpha. These transmutation reactions are used indirectly to detect neutrons, which you'll learn more about tomorrow. They have a very high Q value, so the energy released from this reaction is quite high and makes it easily measurable with electronics. And the cross-sections are higher for thermal neutrons, which makes it a much better efficiency than, say, scatter reactions. Sorry about that. This makes the momentum and energy balance important in detector design, and we'll do a quick example here on how you could know the energy of the triton and the alpha from this transmutation reaction. It's got a Q value of 4.78 MeV, which you'll need for this example problem. So remember your conservation of energy and conservation of momentum. I'll go through the example too, but I'm sure some people know it off the top of their head. But a thermal neutron in this case, so it has a kinetic energy of 0, is captured by a lithium-6 nucleus. What are the maximum and minimum energies possible for the reaction? A few hints here. The mass of the triton is equal to about 3 neutron masses, and then the mass of the alpha is equal to about 4 neutron masses. So based off that, apply conservation of energy and conservation of momentum to estimate what the energy of the resultant triton and alpha are. And again, we have that Q value of 4.78 MeV, so that's how much energy is being distributed between the two. I'll give you guys a few minutes to try out that example, and I'll wait for an answer or two in the chat, or 5 minutes at the most. Feel free to ask a question this time as well if you need. Just put it in the chat. I think it's been about 3 minutes. Are there any guesses in the chat? I'm not seeing any, but that doesn't mean that my Zoom is being perfect. If you're working on it, let me know. All right, we're approaching that 5-minute mark. I don't see any answers in the chat, but I'll just go ahead and start running through the solution. Oh, sorry, I see one question from Saif. Is that plus and minus 0.08? Not quite. I'll go through the solution and hopefully that'll help you out. Another one. The kinetic energy of the hydrogen is E equals 2.72 MeV. Nice job, Aiden. I'm pretty sure that's correct, but we'll go through the solution and double check. There we go. So we start with our energy balance. On the left-hand side, we just have the initial energy of the neutron and the Q value of the reaction. And because we're looking at a thermal neutron, the energy is about 0. So we can exclude that, and we say the energy of the triton, in this case, is equal to the Q value minus the energy of the alpha. And we'll be using that equation later. Apply conservation of momentum, mv equals mv. And then we know about the mass of each isotope here. And then we know how energy equates to the mass and the velocity. We're not in relativistic world, so we're just using classical kinematics here. And we see E equals half mv squared in the classical sense. And then we can just apply the substitution into our momentum equation and have a relation of the energy of the two particles. From this derivation, we can solve for the energy of the triton, and it's going to be weighted by the weight of each particle. And we see on the bottom right here that the triton ends up being equal to about 4/3 of the alpha energy. And you can come back to this recording too if I'm going too quick for you. And then from that, we can substitute back that equivalency into our energy equation. And we get the triton again equals 4/3 of the alpha energy. And then we know our Q value. So we know the Q value is equal to 7/3 of the alpha value when we do our substitution. And then we can convert that so the alpha equals 3/7 of the Q value. And the energy alpha is 2.05 MeV. And the energy of the triton in this reaction is the remaining energy from our Q value, which in this case is 2.73 MeV. So yeah, we were within rounding there, Aiden. Nice job. So we talked about capture transmutation. You all worked through an example. Feel free to come back to the recording too if that wasn't quite enough time, and you can practice it on your own. There are also plenty of resources I'll provide at the end that also have example problems like these. And last one we'll talk about is induced fission. We talked about spontaneous fission earlier, but I didn't tell you as much about the reaction and how the fragments occur, so we'll talk about that in a moment. But induced fission is when an atom absorbs a neutron, causing excitation, and then it de-excites by splitting into two fragments. And those fragments themselves can also be excited and continue to decay. And then we also get neutrons from the immediate induced fission reaction. So here's a quick summary of induced fission. It's most probable at those thermal energies, so lower incident neutron energies, for uranium-233, uranium-235, and plutonium-239, which are important isotopes we'll talk about more later this week. The number of neutrons and the identity of the fission fragments differ from reaction to reaction. I show you one specific reaction here on the bottom. A neutron is incident on uranium-235. It's absorbed. That should actually say uranium-236, my apologies. And then it splits into a barium and a krypton and emits 3 neutrons. The neutron emission is not always going to be the same for every reaction, even this barium krypton split, because you can also produce a separate amount of gamma rays, et cetera, et cetera. But we see 3 prompt neutrons emitted, and then these fission fragments can also go on to emit gammas, delayed neutrons, et cetera. But we can see on the top right here, sort of the distribution you can see from these induced fission reactions. So you see sort of what looks like a saddle shape for the resultant fragments from fission. We saw here the barium and krypton, which matches up pretty well to the peaks of our saddle. We have 144 on the right and 89 on the left. But we can get several other combinations from fission. You see this saddle spectrum for U-235 fission when it's a thermal neutron, so the most likely interaction that we just described here. We really get the saddle shape where we have this sort of distribution of our fragments, and they stay relatively the same. But as our neutron energy increases, that saddle actually starts to level out. So you see in blue there a 14 MeV incident neutron distribution. So we start to see a bit more equal fission fragment sizes, but it's still predominantly the large and the smaller fragment. Sorry about that. So I've talked a lot to you about reaction likelihoods. I wanted you to get an idea of reactions themselves and what they are with the neutrons. But we'll go back here and we'll talk about what are called cross sections, which directly quantify the reaction likelihood. And we'll do one example here as well. But the microscopic cross section is a quantity that describes the likelihood of a specific interaction. It's in this unit of Barns, which is a unit on the atomic scale of area. 1 barn equals 10 to the negative 24 centimeters squared. And if you have a neutron incident on a nucleus, the nucleus is very, very small. Stefano described this in his previous lecture, but the area scale is even smaller than a barn for a nucleus. But depending on the type of particle that's incident and the type of nucleus it is, it's not going to see the same area every time. So that's why it's more of a likelihood than a physical quantity. But you can see here just a diagrammatic explanation of what the cross-section looks like. We represent it with this Greek letter sigma, lowercase sigma, and it's just a fraction of an area incident. You can have cross-sections for several different types of reactions. We can have the cross-section for scattering, cross-section for absorption, and then those can be broken further down even into elastic, inelastic, neutron, gamma, fission reactions, etc. I see a question in the chat. Oh, good question, Ben. I'll get back to that. And the probability of a specific interaction can then be expressed as that specific interaction type, so elastic scattering, inelastic scattering, or you can go more general, scatter absorption over the total. And the total cross-section is still a likelihood within itself, but when we go into the subreactions, you can quantify them over the total. There we go. So to continue, we talked about the microscopic cross-section, which is this quantity in Barnes, which describes the likelihood of a specific interaction for a single target nucleus. Sorry, typo there. And macroscopic cross-section is a quantity that describes the likelihood of a specific interaction for all nuclei in a given volume. So we're talking about this Barnes scale for microscopic. It makes a lot more sense when we scale it by the density of a given material. So that's what we're doing here. it's equal to the microscopic cross-section times n, where n is the atomic number density, or the number of nuclei per meter cubed per unit volume. We can apply this in different scenarios like neutron attenuation. We can also apply it for those reactions we talked about earlier to get reaction rates, but we'll go through an example here on neutron attenuation. If I have some sort of beam, we talked about the DT fusion generators earlier that cause a beam of neutrons. We can attenuate that with material. And what you're seeing here is the incident neutron beam density, I on the top, and I not on the bottom, and the resultant neutron beam density, I on the top. And this is directly related to the cross sections at E, or exponential of the negative total cross section times the thickness. And you can apply different reaction types as well if you don't want to look at the total reaction. But then we can change the macroscopic cross section to the microscopic by including the number density, or n. And we can also quantify this cross section as a mean free path, or lambda. And it's the same as 1 over the macroscopic cross section, or 1 over the quantity sigma times n. It quantifies the distance traveled by a neutron and a material before an interaction on average. So we'll get to an example here. This one's on cross sections and neutron attenuation. Consider a thermal neutron, so 0.025 MeV, neutron beam incident on a thick uranium-235 metal slab. The total interaction and fission cross sections for a neutron of this energy are 689.7 barns for the total interaction and 582.2 barns for the fission interaction. What distance would a neutron travel before any interaction, which corresponds to the total, and before a fission interaction on average? So I'm doing this example here, a bit of a start for you to get you the number density, but from there, I'll give you a few minutes to get the mean free path that I described earlier. And I'll go back to those equations as well, but go ahead and take a chance to write down the number density. The way we go about deriving that is we take the density as we more commonly know it in grams per centimeter cubed. So in this case, it's 19.1 for uranium-235. And we multiply that by Avogadro's number and divide it by the molar mass to get it in units of atoms per centimeter squared. So this number is 4.9 times 10 to the 22nd atoms per centimeter cubed, sorry. And take a moment to write that down. We'll go back and you can use that number and the 689.7 barns for the total cross section and the 582.2 barns for the fission cross section to get the mean free path for each type, the total mean free path and the fission mean free path. So just take a chance to write those down. Sorry, I keep moving from Zoom to PowerPoint. And then I'll show you the solution in a second, but you can plug it into this equation here. While you guys are working on that, I'll take a moment to answer Ben. Ben asks, why does neutron interaction cross-section change with neutron energy? And does interaction change proportionally the same for different nuclides with varying energies? It's a great question, Ben. So it's highly dependent on the isotope you're looking at. That's part of the second question. And the neutron energy changes the cross-section. When you have I'm not a physics expert, so you don't have to take everything I say here at face value, but as I generally understand it, when you have neutron energy and you're associating it with a cross-section, say on uranium-235 for fission, it's much more likely to cause fission at thermal energies because the wavelength of the neutron is such that it overlaps quite a bit. It's a much larger, it's a much larger wavelength that can overlap with the nucleus that it's interacting with. Once you get to those faster energies, you're talking much quicker wavelengths, and it's a lot more likely to pass through the material. Those fast neutrons just don't interact with much of anything at all. They're a lot more likely to pass through feet of concrete and things like that. But the thermal neutrons will be easily stopped by things like water and other nuclei. The second part of the question was, does the interaction change proportionally the same for different nucleides with varying neutron energies? When we talk about fission, we see pretty similar distributions for the neutron cross-sections over energy for uranium, plutonium, etc. And we also see these resonance regions. They're not exactly the same, the change over energy, but the general trends are similar. The magnitudes are slightly different. Thanks for those questions, Ben. So now that I've been rambling a bit on Ben's question, I hope you had some time to try out the neutron attenuation, so we'll run through that example. So given the inputs, the total cross-section of about 690 barns and fission cross-section of 580 barns for this thermal neutron on U-235, and we know the number density, 4.9 times 10 to the 22nd atoms per centimeter cubed. We can get the macroscopic cross-sections for each. The macroscopic total cross-section, we convert barns to centimeters squared. We multiply that by our number density, and this gets us 33.8 centimeters to the -1. For the fission cross-section, we do the same process, and the fission cross-section is lower, as we would expect. It's not the only reaction, but you can see here by the ratios that it is the main reaction. The total macroscopic cross-section for fission is 28.5 centimeters to the -1. We take the inverse, we get our mean free path, and the total mean free path in the fission slab is only 0.03 centimeters. And that's because thermal neutrons are just very likely to fission in uranium-235. If we had the fast cross-sections, those would be on the scale of barns, and it could travel more like centimeters or so through the material. The same thing goes for the macroscopic cross-section for fission. It can travel a little bit further because the macroscopic cross-section is lower. It can travel up to on average, 0.035 centimeters. And with that, I've filled up your 45 minutes, but happy to take any more questions like Ben's and answer them to the best of my ability. Thank you for coming to the lecture. And tomorrow, Julian Lampro will be giving you a nice talk on neutron detection. And we'll take a lot of these reactions that we've learned and show you how they're applied to radiation detection. I'd just like to acknowledge the consortium for supporting this work. And fair use disclaimer, we have plenty of material that's used from other sources here, but it's all for scholarly purposes. And there's also a few references at the end of these slides that you can come back to, pull them from the recording. Specifically, one of my favorites for neutrons is the Panda Manual. It summarizes a lot of these reactions and how they're applied. You can use this for the detection lecture tomorrow and the non-destructive assay lecture we have on Thursday, as well as null. Great info for anything detectors. You can use that for Gamma Week last week and weeks upcoming. And NIST, that's where we pull a lot of the nuclear data from. And the APS as well has plenty of fundamental neutron physics you can look more into.
Thank you, Mr. Flynn, for this great presentation.
Thank you. Great question, Ben. Yes. What is my opinion on the island of stability? Do you think that ultramassive isotopes will someday be made? Um, I can't say that I know a ton about the island of stability, but I have a decent idea. And I have been to Oak Ridge, where they've patented their Tennesseum, just making a bunch more huge elements. I forget the neutron number for that one. But my opinion on that is we probably still have a little ways to go. We're making huge facilities that have higher neutron fluxes, that will potentially have higher neutron fluxes than current facilities do. So we might not be quite there yet. It'd be interesting to see if we could probe high neutron fluxes like the sun and find what the true island of stability is. But yeah, I don't know if in my lifetime we'll reach that. Great question. Feel free to ask any other questions. I'll be in the chat here until 1:50.